Okay, so we're going to continue our energy notes. This is part 2. I know it's been a little bit longer. This is one of the longer videos. I promise to try to make it as short as I can, but we still have to get the information to you, right? Again, you're learning this, and then you're going to bring questions into class, and we'll learn a little bit more as we need to. So try your whisk really well at the end here. So we are using that equation that we just learned at the end of the other video here, part 1, is that the internal energy, or the change in energy, okay, is equal to the heat, Q. Can't do that at the same time. Sorry, I didn't finish energy over here. Whoops. And adding to the work. Now we have to remember to watch the signs, okay? So they could be different signs, and also they have to have the same unit. That's what I want to make sure that I emphasize here. Okay, now the signs could be different. I could have a positive or negative of either of them. So I have to watch that. That's where most of the problems become an issue there, okay? So calculate the internal energy, so delta E. If a system absorbs, okay, now let's read this carefully. 51 kilojoules of heat absorbs, okay? What does that mean? It's going to come into the system and be positive. And it does, watch that word, 24,000 joules of work on the surroundings. So it's working. If it's doing the work, that is going to be a negative W. Okay, so this is heat, Q, and we have a positive W. So just to make sure that we understand how to do this, I'm going to write the equation real quickly just so I get this in the right order or in the right way. I mean, you can add them either way. It doesn't matter because Q plus W or W plus Q does not matter. But our Q is positive. So I'm going to write very clearly that it is a positive, how many? 51 kilojoules. And it's going to be added to, we have our work now. Our work here is negative. So we got to be careful. It's adding a negative 24,000 what? Joules. Now, there's a couple issues here, and I really didn't leave enough space. Now that I notice it, right? What is happening here is that we have kilojoules and joules. Okay, so they are not the same unit. They need to be. So does it matter? Did it ask me how much the internal energy? Did it say I had to go to kilojoules or joules? No. So we could go to either. I'm just going to choose to go ahead and go back here. I know that's not the most beautiful way to do it, but I'm going to leave it as positive 51 kilojoules. And I'm going to convert the work to kilojoules. So kilojoule is 1,000 joules. So we got to go back because kilojoules are bigger. We kilojoule and go back 3 places. And that is 20. Whoa, we got to put the negative. Do not forget that. That is crazy. 24 kilojoules. Okay, so I converted the 24,000 negative joules to negative 24 kilojoules so that I can now add, and that now is 51 minus 24, which is a positive value more because we have more positives, kilojoules. Okay, so 27 kilojoules is my answer. Now, I'm sorry that I went forward and then backward, so hopefully you'll follow that and do that even better yourself. So we have another one here. I'd like you to pause the video right now and try it yourself and then come back and check. All right, so hopefully you've done this. It says calculate the change of energy. So again, do I have to write the formula? No, I know I'm just going to add the heat and the work, but for a system that performs work on its surroundings. So again, we are doing work. So that means this is a negative W, all right? And loses 65 kilojoules. So we're going to be negative Q, negative heat. So we get negative of both because we're doing the work, performing the work on the surroundings. We are also losing the heat or letting it go. So when we put these into our equation, the Q is negative 65. And again, we could have done it either way. We do want to pay attention to our units. I don't know if they're the same yet. I'm just going to write them down. Negative 65 kilojoules. And then my work is negative 20. It is also kilojoules. So that makes me kind of happy because all I got to do is add these negative numbers. There's 2 negative numbers. So again, it's going to stay negative by adding them together. And that is 85 kilojoules negative. So exothermic, we're losing, whereas this one is endothermic because we're bringing heat into the system. All right, so hopefully you'll be able to do that. You'll have one practice in your whisk coming up. And again, just watching. It's just about adding, but making sure your signs are good. Okay, one more concept here before we are done. We have two types of energy that we've been talking about, kinetic energy and potential energy. Together, they're actually called mechanical, just as a side note, energy. Now, kinetic energy, we already talked about that it's the energy of motion, okay? When the molecules are moving, that's what we're measuring when we get the temperature in the morning, right? The average kinetic energy. Kinetics are studied with anything that moves, like hands and legs and feet and how you should run. So there's a big study, like a physical therapist or doctors and stuff like that want to learn a subject called kinesiology. Kinesiology studies the movement of your body, how it should move, so that we can fix that if there's issues, right? So anyway, we have lots of uses of kinetic energy, of course. Kinetic energy, you're going to abbreviate KE, and there's a formula for it. It is 1/2 mv squared. Well, what is m? Of course, mass. It has always been. Now, there's a little caveat here that you have to be very careful with. This mass must be in kilograms based on the unit joule. Okay, so we're going to have kilograms. And then this v here stands for how fast it's moving, the velocity. Okay, so velocity. And velocity is meters per second. All right? So, but that is squared. Now, realize this. The velocity is squared. Okay, so the unit, you're going to square that, but you're squaring your number. So if it's 3 meters per second, that is going to be 9. Okay, so we square first. We have to follow the order of operations. Please excuse my dear Aunt Sally. So squares are exponents. Then we're going to multiply and divide, or whichever way. Okay. So we can solve those problems in just a little bit. So the unit is actually considered a kilogram meter per second, but actually it is squared. Okay, so it is that unit does get squared too, and that is then equal to a joule, because that's a Newton meter. It's kind of a crazy little thing, but just as long as you know the joule, you're fine. All right, so potential energy. Potential energy, you have a lot of potential. Everybody ever told that? Like, you're not actually using it, you just have it stored, or it's in position. So a lot of times they'll use the word position or stored energy. So when we're talking about the roller coaster at the very top, it's got the position, it's ready to go, it's soaring it up to get, there we got that change, okay? So potential energy, many examples in the real world, of course, just put a stapler at the edge or anything on an edge of anything, that's going to have the position and ready to go to kinetic or whatever, but it's position. So I use the formula, or everybody does, sorry. I say it though, MG, like you got potential, dude, and you're going to sitting there going, MG, like duh, but MG. I know it's a little weird, but I like it. It helps me remember it. So MG stands for M is mass. Again, everything's dependent on mass here with energy. And once again, it has to be in kilograms, guys. So watch that. If I give you grams, you have to convert it to kilograms to solve. Now, the G stands for gravitational. So this is potential energy due to gravitational acceleration. There are all types of potential energy that we could get into in physics if you ever take it. But gravitational acceleration, it actually has a value. This is pretty interesting. It is a constant. Okay? Constant means you'll always know this number. It's like we're doing a skiing race, or I don't even know, any kind of race, and you're getting a score, you're always going to get a 9.8. Now, this is where chemistry and physics kind of differ, and when we calculate this, a lot of physics will just estimate and say, okay, well, we're round to 10, but we do not do that. We like sig figs. We want to be able to measure. We could, it's a matter of life and death for a lot of situations. So 9.8 meters per second squared, you will always know that unit. All right. And then lastly, we have H. H is for the height. So when we talk about position, how high is it off of the ground or surface or above gravitational pull? Height is going to be in meters. So once again, we have kilogram meter squared per second squared. So the unit is a joule. All right. So we know that both of our units are joules. It's just how we get there. So let's go ahead and put these into use. We only have 2 more little problems here to show you, and then you're going to try an internal energy and a kinetic energy, and then later on we'll do potential, of course, on your Smart Start, and we'll try different problems, right? So this one says to calculate kinetic energy. So when I know I've got kinetic energy, what am I going to do? I'm going to write down the formula, 1/2 mv squared, all right? And then I'm going to find those numbers. So we have a 60-gram object, that's a mass, moving at a velocity, wow, it's just telling me, it's like crazy how easy they're making it, right? Velocity of 5 meters per second. So we're going to go ahead and plug these numbers in. Of course, the 1/2 is just there. The mass, I got 60 grams, can I use grams? I told you, no, you have to go to kilograms, okay? So you can do the conversion, but I think most of us can do this in our heads now. 60 grams. Kilograms are are bigger units, so you need less. I meant to say that in a different way. So a kilogram is going to kilogram, meaning we're not going to have as many, so there's 60, but we're going to go back 3 places, so that is 0.060 kilograms. Now, if you need more help converting, you're going to have to come up and ask me, okay, on an individual basis. So again, 1,000 kilograms. You could come to the side and do what we've been doing all the time is factor label grams to kilograms. You have 1 gram, 1,000 grams in a kilogram. That means you divide by 1,000, so that's why we get that. So we're going to plug this in. We use 0.060 kilograms. Actually, it's 00 for sig figs because we had 3. And then we're going to multiply by, now we're plugging in the velocity. The velocity is 5.0 meters per second squared. Now that is what? Squared. Okay. I meant to say it's not meters per second. It's just meters per second and then square it. Sorry. Woo, almost lost it there this morning. So what are we going to do? We got to solve this. So I'm just going to write it a little bit slow here. We're still going to keep everything here the same, the mass and the half, okay? But we got to do this first. We got to square that. So 5 squared, 5 times 5 is 25, all right? And that is going to be, you don't even have to worry about the units, but it's meters squared per second squared because it did get squared also. But then don't even really pay attention to that because you'll mess yourself up as long as you just have the kilograms there, okay? So now we just take 25 times 0.06 and then take half of it. A lot of people leave out the half on accident. If you do all that, you're going to get 0.75 joules. And we circle that answer so we know where that is nice and neatly, and we write the joules a little better there. Because I only went to 2 sig figs because of the velocity limited me to 2. All right, any questions you're going to have to ask me in class. And lastly, let's do a potential energy. We have a potential energy problem, PE. Potential energy is MG, one of my favorite to say. MG. So we're going to go through and see what we got. We have a kilogram object. Ooh, that's nice because we won't have to convert because we know we need kilograms. There's the mass, and it's in the right place. And then 1.5 meters tall that is sitting on that desk, that is the height, right? And it's already in meters, which is what we want. Now, where's the G? G, remember what I told you? We already know that every time, okay? So we're going to go ahead and just plug these things in. We have the mass is equal to 13.0 kilograms. Beautiful. I don't have to do anything because it's already in kilograms. The G, I just write it down. It's 9.8 meters per second squared. And now we have the height, which is 1.5 meters. So now you can see where the meter squared, second squared comes in again, kilograms. So it's just joules. And so everything is working together. We just multiply everything. I'm going to go a little bit harder on sig figs here that we're going to get 191.1, and it is joules. You just go ahead and put joules every time for any of these energy units. How many sig figs? We only have 2 here again. So this one's a little tougher in that we can only keep the first 2 digits here, but we still have to take the place. I can't say 19. 19 is nowhere near 191, so I got to hold that place without putting a point, not making that significant. So it's 190 joules straight up. All right. So let's do those whisks. Show me what you know or what we need to go over in class and ask questions as needed.